Swayam Prabha. Digital India. Educated India.
Good morning and welcome again. After having discussed B-spline basis functions at length, we now would start our discussions on B-spline segments and curves. This is lecture number 29. Let's first start with the definition of B-spline segments. Given n plus 1 control points b0, b1 up till bn, and also a knot vector capital T as t0, t1 up till tm, a B-spline segment or curve b of t of order p is defined as b of t is equal to summation the index I going from 0 to n, the normalized B-spline basis function n sub p, p plus I of t times bi. Now, if you notice, this is a very similar construction as we have seen in case of Bezier segments. There we had Bernstein polynomials. Here we have B-spline basis functions acting as weights for each design point that a user would specify. Let's look at some graphics. So we have a bunch of knots, T0, T1, T2, up till, let's say, Tp. We continue. Tm minus p, Tm minus p plus 1, up till Tm. We observe this knot vector going from T0 to Tm, T0 to Tm. The first basis spline function will be npp corresponding to I equals 0. That would be spanning over the knot span T0 to Tp. The second one will be spanning over T1 to Tp plus 1, and it will be nomenclated as np p plus 1 of t. Likewise, the third one will be named np p plus 2 of t. We keep on continuing until we plot the last basis function, of which the last knot is Tm and the first knot is Tm minus p. This is, of course, np p plus n of t, which is the same as np mt. Note the last knot over here, tm. This p plus n index corresponds to I equals n. Now, if you notice, with each of these B-spline basis functions or weights, a design point bi will be associated. Now, a B-spline segment is very similar to a Bezier curve or a segment wherein the basis functions are the Bernstein polynomials. I've mentioned this before. This is the definition of a B-spline curve or a segment. In a Bezier curve, the degree of the Bernstein basis functions is the same as the number of control points. Here, however, the degree or the order of the B-spline basis function p is independent of the number of control points. In a sense, p is not dependent on n. For B-spline curves, the degree of the basis functions is an independent choice, therefore specified by the user. The number of knots, which is n plus 1, if you recall, the knot vector goes from T0 to Tm, gets determined by the relation m equals n plus p. P is the order of the B-spline basis functions, and n plus 1 is the number of design points specified by the user. Accordingly, the number of knots get determined. This is what I just said. The total number of basis functions, n plus 1, is equal to the number of control points, and p, this should be small p, is the order of the basis spline functions and hence the curve. Let's now discuss the parametric range of a B-spline curve. This is a figure I have borrowed from 2 slides before. These B-spline basis functions, npp, np plus 1, np plus 2, up till np plus n. How many are these? Of course, n plus 1. Now, a B-spline curve definition is valid for all values of t in minus infinity to plus infinity. Let's take a look at any of these B-spline basis functions, np, p plus 2, for example. Now, for values of t smaller than t2, np, p plus 2 is 0. And for values of t greater than this knot here, again, np, p plus 2 will be 0. So, in effect, np, p plus 2 of t is valid for all values of t in between minus infinity and plus infinity. And the same is the case for all these basis functions. And therefore, since B-spline curve is a weighted linear combination of these functions, it will be valid for the entire range of t. Clearly, b of t, the spline segment, will be equal to 0 for values of t smaller than t0 and for values of t greater than tm. And so, the range of t in between the values t0 and tm seems reasonable. Let's look at a slightly more restrictive range. That would be the one in which full support of the basis functions is achieved. Now, what do I mean by full support? Over any knot span tj, tj plus 1 in t sub 0, t sub m, all p B-splines of order p are non-zero. If that is the case, then we say we have full support of the B-spline basis functions. The first such span would be Tp minus 1, Tp, which is this one here, where npp, npp plus 1 up till np 2p minus 1 are non-zero. These are p B-spline basis functions which are non-zero over this interval here. So, this would be the first span to include all p basis functions. Likewise, the last span to include all p basis functions will be Tm minus p, Tm minus p plus 1, which is right here. Over this knot span, np m minus p plus 1, np m minus p plus 2, and so on up till npm will be non-zero. So, this is the last span to include all p basis functions. So the range of definition of a B-spline segment will be given by up till t m minus p plus 1, wherein for any t, for any value of t, all p basis functions are non-zero. That means for values of t in between t to t m minus p plus 1, over this interval, we will be able to achieve full support of B-spline basis functions. And this would be the parametric range of a B-spline curve. For data points 0, 0, 0, 1, 2, 3, 2.56, 5, 2, 6, 0, and 7, minus 3, let's design a B-spline segment. We have the number of data points as 1, 2, 3, 4, 5, 6, 7. Let's design an order 4 B-spline curve. We have to specify the order here as an independent choice. Correspondingly, the number of knots will be the number of data points, which is 7, plus the order of the curve, which is 4, and that will be equal to 11. It is up to the user to specify the values of the knots, T0 up till Tm. Here, we choose to work with uniform knot span. T0 is 0, T1 is 1, and so on up till T10, which is 10. These are clearly 11 knots. Now, this knot span here, that starts from T3 equals 3 and ends at T7 equals 7, is the range of full support. Over this knot span, for any value of t, we will have at least 4 order 4 B-spline basis functions to be non-zero. We have seen this definition of B-spline segment. B of t equals I going from 0, 6, n p plus I of t times bi. Now, if you note, b sub I is ordered. It's a vector. Here p equals 4, and this value 6 corresponds to the number of data points 7. Let's look at the graphics now. We plot these data points and the associated control polyline. Now, what you see here in blue is a B-spline curve for values of t in between 3 and 7. Now, let's experiment a little bit. What we do now is we change the knot vector slightly. We replace this knot and this knot by 3. In a sense, we increase the multiplicity of T3 to 3. And let's see what happens. The B-spline in red now passes through the first control point or the design point. Let's experiment further. Now, we replace these knots T8 and T9 so that T7 becomes a multiple knot of multiplicity 3. What happens then? The resultant B-spline curve now passes through the last design point as well. So, it passes through the first design point as well as the last design point. What if I now make the first knot here of multiplicity 4 and the last knot as well of multiplicity 4. So we have the first knot repeated 4 times and we have the last knot as well repeated 4 times. We do not see any change in the shape of the curve. It passes through the first point, ends at the last point, and it happens to be the same as the one in the previous case. Let's look at some properties of B-spline segments. Now, these properties of B-spline segments, as in the case of Bezier segments, will be dependent very much on the properties of the respective B-spline basis functions. The first one, a B-spline curve, is a piecewise curve with each component an order P segment. This is expected because each of the B-spline basis function by itself is a piecewise curve. Each piece is an order P segment. The equality m equals n plus p must be satisfied. In a sense, the number of knots has to depend on the number of design points as well as the order of the B-spline curve. Strong convex hull property. The B-spline curve B of t is contained in the convex hull defined by the polyline Bj, Bj plus 1, Bj plus 2 up to Bj plus p minus 1 for values of t in Tj plus p minus 1, Tj plus p. In a sense, over each knot span Tj plus p minus 1, Tj plus p, a part of the B-spline curve will lie within the convex hull defined by the corresponding P design points. And this convex hull will be a subset of the parent hull defined by B0, B1 up to Bn, in a sense, all the design points. Let's look at the graphics now. This is the interval of concern, Tj plus p minus 1 to Tj plus p. This B-spline basis function is Np p plus j. The last knot is Tj plus p. This one here is Np j plus 2p minus 1 of t. Now note that this basis function ends at Tj plus p, while this one, Np j plus 2p minus 1 of t, starts at T j plus p minus 1. These are, as we know, p basis functions, which will be non-zero over this knot span. Of course, this is the definition of the B-spline curve we are working with. Now try to figure the design point associated with this basis function and the design point associated with this basis function. Observe that B of I is associated with Np p plus I. So with Np p plus j of t, the design point Bj will be associated. And with Np j plus 2p minus 1, the design point j plus p minus 1 will be associated. This one is right here. So the curve, the B-spline curve B of t for values of t in between Tj plus p minus 1 and Tj plus P will be lying within the convex hull defined by these P control points, Bj up till Bj plus P minus 1. Do you know why this happens? This happens because of the local barycentric property corresponding to these P basis functions. As I mentioned, Bj is associated with Np, P plus J, and Bj plus P minus 1 is associated with this basis function here. We have seen this before, that these P B-spline basis functions are locally barycentric as opposed to global barycentricity, which is exhibited by the Bernstein polynomials. Now, this property has consequences, which we'll investigate now. We continue with strong convex hull property. Let's look at the B-spline curve that we have seen in the previous example. We have the corresponding data points and the control polyline shown in black. Now, this curve here corresponds to the original knot vector, T0 as 0, T1 as 1, up till T10 as 10. There are no multiple knots in there. For values of T in between 3 and 4, a part of the curve will be enclosed within this convex hull defined by the first 4 design points. For value of T in between 4 and 5, the second knot span, a part of the curve will be now enclosed within the convex hull defined by B1, B2, B3, and B4. For T in the third knot span, a little segment of the B-spline curve will be within this convex hull defined by the third set of 4 design points. And finally, for T in the last knot span, the convex hull will be given by the last 4 design points. Now, if you notice, the values of T are in the knot span corresponding to the full support. It's for these values of T where we have all 4 B-spline basis functions non-zero for any T. Now, if you look at the overall convex hull or the parent convex hull defined by all the design points, it looks like this. And let's superpose the previous convex hulls that we have seen. Now, you would note that if you combine all these convex hulls together, the area formed will be smaller than the area of the actual convex hull or the parent convex hull. What would this mean geometrically? This would mean that our B-spline curve will be kissing the control polyline more proximally compared to a Bezier segment, which is why we mentioned that this is a strong convex hull property. A B-spline curve, B of T, is C P minus K minus 1 continuous at a knot of multiplicity K. This is expected. Why? Because each individual B-spline basis function exhibits the same property. And since B of T is a linear combination of those basis functions, it has to have the same property. At T equals Ti, which is a knot of multiplicity K, since NPI of T is C P minus K minus 1 continuous, so is BT at that knot. Now this one is the next one, local modification scheme. Relocating BI, a design point, only affects the curve BT in the interval Ti plus P. And this is again a result of the local barycentric property demonstrated by the B-spline basis functions. Like in the case of Bezier segments, let's do the following analysis. Let the control point Bi be moved to a new position Bi plus V. So the new B-spline curve C of t is given by the index k going from 0 to I minus 1 n p plus k of t times b of k plus n p plus I of t bi plus v. Now this is the new location of the control point Bi plus k going from I plus 1 to n p plus k of t times bk. Now let's extract this term out and add to this and this to give us summation k going from 0 to n p plus k of t times bk plus n p plus I of t times v. This is our original B-spline curve with an additional term np plus I of t times v. Now observe for what values of t would this term be non-zero. Clearly np plus I stands over the first knot as ti, p plus I minus p, the last knot as ti plus p. So for values of t in between ti and ti plus p, this term here will be non-zero. This is the interval. So in a sense, the shape of the curve will be locally influenced only for values of t in this interval. Otherwise, the shape of the B-spline curve will remain unchanged. np I plus p of t is non-zero in ti plus p. For t belonging to this interval ti plus p, p of t, our B-spline curve, will get locally modified. Let's work with the same example. Our design points, the control polyline in red, and blue here is the B-spline curve corresponding to the uniform knot span with all simple knots. If you recall, the knot span that we had used was from 0 to 10. Now let's relocate this point from here to here so that the control polyline changes a little in green here. What will happen, do you think, to the corresponding B-spline curve? Now if you notice, the new one in dashed green gets locally modified in shape. Only the portion corresponding to this part gets modified, whereas this portion here remains unchanged in shape. Now this is a feature that we did not see in two cases, one for Ferguson curves and the second for Bezier curves. But now with local barycentric property, associated with B-spline basis functions, we can think of modifying the shape of the curve locally now. Let us now implement whatever we have learned so far to try to understand how to design B-spline curves. Design features with B-spline curves. Now, shape manipulation of B-spline curves can be done using either control points or using the knots. When working with control points, we can use the strong convex hull property. And when working with knots, we can use knot multiplicity. We can also use the positions of knots, but that is not a good idea. Changing the position of knots can cause shape change, but it is not intuitive and therefore it is avoided. Now for the shape change using control points. Recall the strong convex hull property. The B-spline curve B of t is contained in the convex hull defined by the polyline bj, bj plus 1, bj plus 2, and so on up till bj plus p minus 1 for values of t in the interval tj plus p minus 1 to tj plus p. And of course, this convex hull is the subset of the parent hull given by b0, b1, b2, bn. These are the design points that you may have specified. Now the question, what if bi, bi plus 1, bi plus 2 up till bi plus p minus 1 are all in a straight line? Don't get confused. All we have done here is we have changed the index. So the question again, what if these p control points are in a straight line? Remember, p is the order of the B-spline basis functions and therefore the B-spline curve. Well, you would realize that the curve segment lying in the convex hull for t in ti plus p minus 1, ti plus p will be a straight line. Clearly, when the convex hull degenerates to a straight line, so would a part of the curve within that also. The second question, what if p minus 1 of these control points are identical? Let's say bi is equal to bi plus 1 is equal to bi plus 2 and so on, and so is bi plus p minus 2. So only one is not identical amongst these design points. Now you would notice that the convex hull degenerates to a straight line bi, bi plus p minus 1, and the curve now passes through bi. Now what if bi minus 1, bi equals bi plus 1 equals bi plus p minus 2 and bi plus p minus 1 are collinear? Now try to understand the difference here between these two cases. Here we have said that p minus 1 of the control points or the design points are the same. Now those design points, a prior point bi minus 1, this point is prior to bi, and then the last point in this set bi plus p minus 1, what if they are all lying in a straight line? The line segment bi minus 1, bi plus p minus 1 is now tangent to the curve at bi. Now all these questions are easily answered once we understand the strong convex hull property. These are the three answers that a designer would want to keep in mind when designing B-spline curves. Let's see a few cases. For the first case, we have p collinear data points. We work with the same example that we have been working so far with. This is our B-spline curve corresponding to uniform knot vector, T0 to T10 as 0 to 10 respectively. Now what I've done is I have moved this point over here. I have moved this point over here, and I have moved this point over here, so that the first 4 design points now lie on a straight line. How do you think the curve would change in shape? This is our new control polyline now, and this one would be the new B-spline curve. You would realize that a part of it forms a straight segment. This is because the convex hull defined by these 4 points degenerates into a straight line. Now, the second case, where p minus 1 data points or design points are coincident, that is, they are the same. Let's look at the same example now. This was the original B-spline curve. I move this point to coincide with this design point here. This one again to coincide with this design point. So remember here, this is an order 4 B-spline curve. P is 4 for us, p minus 1 is 3, so we have 3 design points which are coincident now. What happens in this case? Now the polyline in green is a new control polyline. And this is a new B-spline curve. You would notice now that it passes through this point, which is a multiple design point now. The third case, where we have p minus 1, in our case 3 coincident design points or data points, with points on left and right collinear. We work with the same example. We merge 3 intermediate design points together so as to take care of this condition here. And we move the next point to lie along this line. Once again, we move this point here so that these 3 points are collinear, with this being a multiple design point. This is our new control polyline here, and this is the new shape of our B-spline curve. Notice that not only is the curve passing through this multiple design point, it is also tangent to it, rather tangent to the control polyline. clamping using data points. Now just observe what is happening here. I can make a B-spline curve pass through a design point if I raise the multiplicity of that design point suitably. We use the same concept here to clamp our B-spline curve at the two endpoints. We are working with this example throughout. I move the second design point to coincide with the first one, the third design point again to coincide with the first one. So this is my new control polyline in green, and this is the shape of the resultant B-spline curve. Clearly, it passes through the first point. What is the multiplicity of this design point? Let's go back and figure this out. Two design points coinciding, three design points coinciding. The multiplicity of this control point is 3 in this case. So remember, we are working with p minus 1 multiple design points. It's because of this that our new B-spline curve passes through the first design point. Let's experiment further, and let's merge the last 3 control points together so as to raise the multiplicity of this design point by 3 as well. This is our polyline, and the curve in blue is the new B-spline curve. You would not be surprised that this passes through the last design point as well. How about designing closed B-spline curves using control points? So far we have been working with open curve shapes, in that these curve shapes were not forming loops. Now let's design B-spline curves to form the desired loops. And of course, we are going to be using control points. Let me move one of my data points from here to here. Another one, so that this point here has multiplicity 2. And now this point has multiplicity 3. The next design point goes to a new location. This is another one. Still another one. We keep on doing this. Now, watch carefully what's happening. I generate a new design point to coincide with the first one, which already had multiplicity 3. Second one going there, and the third one going there. So effectively, what has happened? Now the first design point had multiplicity 3, and now the last design point also has the same multiplicity. This is our control polyline, which forms a closed polygon, and this is the resultant B-spline curve. It is because of the first design point and the second design point both having multiplicity of 3 that the curve passes through this point. Now the question, why is it that the curve is tangent to this line, if it is? Let's go back to the previous example. Once again, this design point had multiplicity 3, and so did this. Now, if you bring this one here to coincide with this one here, and imagine that if you had another design point somewhere here, maybe, so that you could have made 1, 2, and this one here collinear, then you would have expected that the curve not only would it have passed through this design point, it would also have been tangent to this control point line here. Something very similar is happening in the next example, right here. You would need a little bit of practice to understand this a little better. I would encourage you to get some. Let's move forward now and discuss shape manipulation using knot modification. Well, this is something that I have mentioned before, that changing knot positions can also cause shape change, but it is not intuitive and therefore it is not recommended. Rather, change in curve's shape if you use multiple knots is predictable. Recall, at a knot I of multiplicity k, the basis function npi of t is cp minus 1 minus k continuous at that knot. Whenever we are discussing B-spline curves, you should keep in mind the basic definition. A B-spline curve, be it a basis function or any other curve, is always Cp minus 2 continuous if it is of order p or degree p minus 1. For simple knots, that is for k equals 1, Cp minus 1 minus 1, Cp minus 2 continuity condition is satisfied for a B-spline curve. Now here is another one. At each internal knot of multiplicity k, the number of non-zero order p basis functions is at most p minus k. By this time, you should be able to figure this property out. All you need to do is sketch the respective B-spline basis functions. Okay, let's see what we have with multiple knots and barycentric property. Let's say we have a set of knots going from T0 up till T10, all simple knots. Correspondingly, we have 1, 2, 3, 4, 5, 6, and 7 order 4 B-spline basis functions. How would you name, for example, this one? This would be N44. Let's concentrate on these red shape functions for now. The B-spline basis functions are named N44, N45, N46, N47 up till N410. You would know now how to do so. So the red ones here are N46, N47, N48, and N49. Now for value of t equals t5, which is right here, N49, this basis function is 0. Now, our interval of concern is T5, T6. Let's concentrate on this interval for now. We have 4 B-spline basis functions which are non-zero over this interval, and because of local barycentricity, all these four functions will sum to 1. At t5, that is at t equals t5, n4, 9 will be equal to 0, right here. So one of the B-spline basis functions will get dropped from the summation. n4, 6 at t5, n4, 7 at t5, and n4, 8 at t5, they will now sum to 1. Let's delve further. A similar case, but now we have t4 equals t5, because of which n4, 8 will be equal to 0. That would make two of the basis splines sum to 1. n4, 6 at t5 and n4, 7 at t5. So observe how not multiplicity is helping us manipulate the local barycentricity property. These are, of course, n4, 6, n4, 7, n4, 8, and n4, 9. Let's go deeper now. Now we have n4, 6, n4, 7, n4, 8, and n4, 9 shaped slightly differently for different cases. Now we have t3 equals t4 equals t5. And this results in n4, 7 equals 0. This would mean that at t equals t5, only n4, 6 will be equal to 1. Okay, so what has just happened? Let me go back. What we did was we tried to raise the multiplicity of this knot over here, t5. We started bringing the knots on the left towards t5, one by one. So at one time we had t4 equals t5, at the other time we had t3 equals t5, and so on. And we observed what happened to this summation over here, or what happened to the local barycentricity property. So for simple knot, n4, 9 is equal to 0. So we have three basis functions summing to 1. When t5 has multiplicity 2, that is when t4 is brought to t5 from the left, the other basis function gets dropped off. n4, 8 would be equal to 0. Consequently, two of the basis functions now will sum to 1. We raise the multiplicity of t5 by 3 by bringing t3 also to precisely lay over t5. This would result in n4, 7 to be equal to 0, because of which only n4, 6 at t5 equals 1. How would this help? Now you would observe that the control point associated with n4, 6 of t is B2. So the 6 index here is P plus I, if you recall. P is the order of the basis functions that we are using to construct our B-spline curves. Because of this local barycentricity property now, you would expect that our spline curve would pass through B2. For this example, in general, if Ti plus 1 equals Ti plus 2 equals up till Ti plus P minus 1, with Ti plus P minus 1 having multiplicity P minus 1, only one basis function, np I plus P, will be non-zero over Ti plus P minus 1, rather at Ti plus P minus 1. And of course, from the barycentric property, NP I plus P will be 1, which would mean that the B-spline curve will pass through the design point BI. Let's now consider an example where we had designed a closed B-spline curve. Recall how we had specified our design points. So we had 3 design points precisely laying over each other at the start, the 4th one, the 5th, 6th, 7th, 8th, 9th, and 3 design points coinciding with each other at the end. So in a sense, we had 12 design points. I would want you to do this exercise with me. Okay, so let's come back. So we had 12 design points. The order of this closed B-spline curve is 4. So we should have 12 plus 4, which is 16 knots in all. So this closed spline is the result when we specify Ti equals I for I going from 0 to 15. So if you notice, these are 16 equally spaced knots. You would guess by now what the range of the full support is for values of T in between 3 and 12. Now at this time, with this knot span, I would want you to sketch all the B-spline basis functions that have been used to design this closed B-spline curve. You might want to take a moment to do that. While you were busy sketching your B-spline basis functions, I was sketching mine. So this is the knot span, T0 up till T15. Uniform knot span with all simple knots at this time. This is the range of full support from 3 to 12. And these are my individual B-spline basis functions. N44, N45, N46, N47, N48, N49, N410, N411, N412, N413, N414, and N415. Now remember, an element in the summation when we define our B-spline curve, NP, P plus I times BI. Try to associate data point BI with the corresponding B-spline basis function. For our case, P is 4. So B0 is associated with 44, N44, B1 with N45, B2 with N46, B3 with N47, B4 with N48, and so on. And in the last, we have B11 affiliated with N415. From B0 to B11, we have 12 design points. Of those 12 design points, 3 of the first ones are coincident here, and 3 of the last ones are coincident at the same site. Though this is a general figure, for our example, B0 equals B1 equals B2, and B9 equals B10 equals B11. 3 of the last and 3 of the first design points are coincident. Now, if I would want to have my B-spline curve pass through this design point, 0, 0, which is 3 plus 4, the 5th design point here, the knot T4 plus 4 minus 1, which is T7, which is equal to 7, should have multiplicity 3. That means the knot values T5, T6 and T7, they should be the same as 7. So my fifth data point or design point is here, and I would want my B-spline curve to pass through B4. That would mean that I'll have to make n for 8 equal to 1. And I'll have to do that by raising knot multiplicity. Now let's concentrate on this knot span T7, T8, over which n for 8, n for 9, n for 10 and n for 11 will be non-zero. Because of the local barycentricity property, these 4 basis functions will sum to 1. Now at t equals T7, n for 11 automatically gets dropped off. Its value is 0 here. So at t equals T7, n for 8, n for 9 and n for 10, these 3 they sum to 1. If I bring T6 to T7, n for 10 becomes 0, and further if I bring T5 to T7, n for 9 also becomes 0, making n for 8 equals 1 at t equals T7. This is when our B-spline curve will pass through the data point B4, which is the 5th data point in our case. Once we do this, this is how our new closed B-spline curve looks like. Now try to work this thing yourself. For this closed spline to pass through this data point here, 8, 0, which is this one, the knot T7 plus 4 minus 1, which is T of 10, which is equal to 10, should have multiplicity 3. That is, T8 equals T9 equals T10 equals 10. Using the similar exercise that we did on board, you might want to confirm this. So notice that this is our 5th data point, 6th, 7th and 8th data point. This corresponds to B7. I'll let you work on the details. I'll just give you the final result. Note that this result does not have the knot T7 with multiplicity 3. This is a different case.